Good morning, everyone. Today, I'm going to present the results of our work on the non-volatile electric field control or spin-orbit torque in oxide 2D gases for developing reconfigurable SOT RAM. So this work was made here in SPINTEC for the experimental part and in close collaboration with the CNRS Thales. So basically, over the last few years, spin-orbit torque have opened a novel way to manipulate the magnetization at the nanoscale using in-plane charge current. If we take heavy metal, for example, large spin-orbit torque were achieved via the spin-Hall effect, which made it possible the rapid development of SOT RAM. In this type of material, however, the sign and efficiency of SOT are fixed by material engineering, which have the drawback of preventing any reconfiguration of the memory. In our team, we are actually interested in a different class of material, the 2D electron gases at the surface of oxide and topological insulator. In this system, the Rajba-Edesen effect allows spin-orbit torque with potentially higher efficiency due to the confinement of the charge current in a very thin 2D interface. And in addition, the possibility of controlling the 2D gas property can be exploited to control electrically the SOT efficiency. There is, in particular, recent work in topological insulator that have shown this possibility of modulation of the SOT efficiency. However, achieving the non-volatility will be a key requirement for bringing this to practical application. So in a previous work, we have demonstrated a large spin-to-charge conversion in oxide 2D gases, along with a non-volatile electric control of the spin-to-charge conversion efficiency. The next step from this will be to achieve the electric control of the mirror charge-to-spin conversion for developing reconfigurable SOT RAM. So in this presentation, I will present the results we obtained on the non-volatile electric field control or spin-orbit torque in oxide 2D gases. So I will first describe our development of perpendicular ferromagnet on strontium titanite oxide, along with the non-volatile electric control of the 2D gas property. And then I will present the results we obtained on electric field control of spin-orbit torque together with dynamical inversion of the SOT sign with voltage pulses. So the SEO whole bar devices that we developed are shown here. The stack consists in a tantalum barrier on top of SEO substrate to protect the 2D gas, a perpendicular cobalt iron boron ferromagnetic layer, and a magnesium oxide layer with a tantalum capping layer. Our motivation for developing COFFEE-BNGO system on SEO is threefold. The first is that COFFEE-BNGO interface has high interfacial magnetic anisotropy to ensure perpendicular magnetization. The second is that the MGO capping has no conduction and no Hall effect that could affect SOT measurement. And last, COFFEE-BNGO is compatible for integration in magnetic tunnel junction for SOT RAM. So we have processed the stack into nanoscale whole bar devices by e-beam lithography for electrical measurement. The temperature dependence of the sheet resistance of the device is shown on the right. A reduction of the resistance by 150% is observed as the temperature decreases, confirming the presence of the 2D gas conduction. And on the other hand, the out-of-plane magnetic field dependence of the anomalous Hall resistance shows a square hysteresis. So this hysteresis here is the signature of the perpendicular cobalt iron boron layer with large anomalous Hall contrast and coercivity of about 29 millitesla. Now, to modulate the 2D gas property, voltage is applied to the device via a backgate. The figure on the left shows the gate dependence of the sheet resistance at 10 Kelvin. An hysteresis with about 1000 contrast is observed in the sheet resistance with two switchable and remnant high and low resistivity state of the 2D electron gas. Importantly, this hysteresis is seen to be inverted compared to usual ferroelectric effect with the switching of the polarization that appeared before crossing the dioelectric field. This is actually possibly due to a combination of ferroelectricity with charge trapping, as it has been observed recently in other systems. As seen on the right, upon increasing the temperature, the contrast reduces and disappears at about 55 Kelvin near the parallel electric-ferroelectric transition of STO. Note the fact that the resistivity of the surface state can be controlled electrically can be used to manipulate the current injection in the 2D electron gas. The current distribution between the two parallel conduction paths, the tantalum cobalt iron boron bilayer and the 2D electron gas, is controlled electrically thanks to the modulation of the 2D gas resistivity. The figure on the bottom shows the ratio of current injected in the 2D electron gas. When in the high resistivity state, no current flow in the 2D electron gas, and inversely, when in the low resistivity state, more than 90% of the current is injected in the 2D gas, which can induce a spin orbit torque. As a result, when increasing the backgate voltage, typical RH loop show a reduction of the ferromagnet anomalous Hall signal, along with an increasing Hall effect in the 2D electron gas. So in which follow, I will present the results of spin orbit torque measurement at this particular temperature, 10 Kelvin, where we can take advantage of the non-volatile electric control of the 2D gas property. To quantify the spin orbit torque, we apply an AC current of 400 microampere at 60 Hz to modulate the SOT amplitude and induce small oscillation of the magnetization around its equilibrium. So this oscillation generates a second harmonic contribution to the Hall resistance, which makes it possible to quantify the spin orbit torque. The figure below shows the measured second harmonic Hall resistance as the function of the magnetic field in the X and in the Y direction at plus 130 volts. If we disregard the opening due to thermal effect, there is an antisymmetric contribution and symmetric contribution that are observed respectively in the X and the Y direction. These are the signature of the SOT anti-damping light torque and field light torque. To extract the spin orbit torque effective field, we fit the first and the second harmonic Hall resistance and follow the Hayashi method, for which the detail can be found in the reference below. Under plus 130 volts, we obtain anti-damping light torque and field light torque of about plus 6.4 millitesla and minus 1.2 millitesla respectively. Now, using the electric control of the 2D gas property, we repeat the same SOT measurement for different backgate voltage. The results show a remnant electric field control of the SOT efficiency with inversion of the sign of the SOT anti-damping light effective field between plus and minus 130 volts. The maximum SOT efficiency is achieved at positive voltage when more than 90% of the current is injected in the 2D electron gas. So here the electric control of the SOT is due to a combination of first, the extrinsic modulation via the non-volatile electric control of the current injection in the 2D gas, and second, the intrinsic modulation via the gate dependence of the bond structure. So overall, the anti-damping effective field per 2D current density of plus 1.6 millitesla ampere centimeter is reached when the 2D gas is in the low resistivity state, which is importantly opposite sign of the SOT in tantalum. So here we demonstrate spin orbit torque effect in perpendicular ferromagnet 2D gas heterostructure and made the first demonstration of non-volatile electric field control of the SOT efficiency. The dynamic control of the SOT is further evidenced below, which displays a normalized second harmonic Hall resistance at electrical remanence after initializing with voltage pulses of plus and minus 130 volts. There is a reproducible inversion of the SOT torque sign that is obtained after initializing with negative and positive voltage pulses. This basically opened the way to reconfigurable spin orbit torque memory. So to summarize, we have developed perpendicular cobalt-iron-boron MgO system on strontium titanite oxide, showing high perpendicular magnetic anisotropy and compatibility for integration in magnetic tunnel junction. A non-volatile electric control of the 2D gas property is achieved with two remanent and switchable resistivity states showing high contrast of more than 1000%. We observe here for the first time current-induced spin-orbit torque in perpendicular ferromagnet STO system with SOT efficiency up to plus 1.6 millitesla per ampere centimeter. But more importantly, here we made the first demonstration of non-volatile electric control of the spin-orbit torque along with dynamical inversion of the SOT sign with voltage pulses. This opened the way to reconfigurable SOT MRAM and logic gate architecture. To go further, more material development can be made to improve the SOT efficiency together with lower PMA for achieving current-induced switching. Also, it will be very interesting to make comparative STFMR measurements of the SOT effective field. With this, I would like to thank you for your attention.